Welcome, everyone. For today's prep, we're going to take a little break from integration techniques, and we're going to start to look at some applications of definite integrals. So our first application of definite integrals is calculating the area between two curves. And we're going to just start with the formula here. So if we have two curves, y equals f of x and y equals g of x, and we want to figure out the area of the region bounded by those two curves, well, we're going to calculate a definite integral. So the area is going to be the integral from a to b of f of x minus g of x. And the key thing here about this formula is that the function we put first has to be the larger function. And then the function we put second has to be the smaller function. So f of x has to be greater than or equal to g of x. And just a little side note here, when we're integrating from a to b, this is kind of giving us the left edge and the right edge of our region. So graphically, let's kind of look at what's going on here. So let's suppose we have our two curves. We have our function y equals f of x, and then we have our function y equals g of x. And if we got x equals a on the left, so that's kind of giving us the left edge here. So we've got x equals a here, and then x equals b over here. So this is giving us maybe the vertical left edge and the vertical right edge over here. So if we wanted the area, let's forget about curve g for a second. If we wanted to know the area under function f, well, this area, as we saw back in Calc 1, this area under f is just the integral from a to b of just f of x. So that's a nice property of definite integrals. That's kind of how we developed the idea of a definite integral as area under the curve. So if we wanted just the area under f of x, we can just integrate our function from a to b. Okay, so, well, what if we did the same thing? What if we forget about function f for a second, and so let's suppose this is function g. If we wanted to know the area under function g, same deal. So if we wanted to know the area under function g of x, we would just integrate from a to b our function g of x. All right, so what happens? Well, when we're trying to find the area in between two curves, we don't want the entire region under function f. We want to throw out this region that's also under g. And this is what's going to give us, get out of the way here for a second, this is what's going to give us our desired region. So when we're looking in between two curves, if we're interested in the region between two curves, we want to look at the region that's bounded above by our curve f, bounded below by our curve g, and then we've got these two maybe vertical lines on the left and the right side. Sometimes it might come to a point. But we've got our x equals a, and we've got our x equals b. So what we want is we want to figure out the area that's under region f, but we want to throw out this region that's also under g. So in math, how do we throw things out? Well, we do that with subtraction. So this bounded region that we're interested in is going to be the area under curve f minus the area under curve g. And we have a nice property of definite integrals that when we have two separate definite integrals like this, and they're separated by subtraction, we can combine them into one definite integral where we have just the subtraction in between the two functions. All right, so little backstory there on where this formula comes from. Not a entirely rigorous proof, but just to give you some idea. Essentially, we're taking the region that's completely under f, and we're cutting out the region that's also under g, the area of the region that's also under g. All right, so the key thing here, though, is, like I mentioned, the order that we put our functions in here matters, because when we talk about subtraction, the order actually matters. So when we do this, the top function goes first. So when we look at our graph, we have to decide which function is kind of higher up on the page, and that's going to be our top function. So when we do our subtraction here, the top function has to go first. Then we also have to decide which curve is lower down on our page, and that's going to be, probably call that the bottom function. And we normally put that second. So again, with subtraction, the order actually matters. All right, so let's try an example. And we'll come back and talk about the strategy. We'll probably do this in class if we have two curves that maybe intersect at one or more points. So then we're going to have to find the intersection points. But let's do an example. Let's look at one nice and clean here where there's no intersection points. So we want to find the area of the region that's bounded below by the curve y equals negative e to the x over 2, and bounded above by the parabola x squared minus 2x. And then we've got our two sides. We've got our left side, x equals negative 1, and we've got our right side, x equals 2. So if we look at our graph for this, what do we see? Well, we see our parabola is the top function. We see our negative exponential function is the bottom function. And then we've got the left edge and we've got the right edge that kind of give us all four sides of this area, this region. So when we go to set up our integral, well, let's start with the limits of integration. So the lower limit is going to be the x value that gives us this left edge. So in this case, negative 1. The upper limit for our integral is going to be the x value that gives us this vertical right edge. So in this case, 2. And then we have to figure out which is our top function and which is our bottom function. So we'll have our top function that will fill in here, and our bottom function that will fill in here. So it's always this, graphically, it's whatever function's higher up on the page. So if we're kind of looking at our graph here, the function that's higher up on the page here is this parabola. It's higher up. So that means x squared minus 2x is going to be our top function. And then the bottom function is whichever graph is lower on the page. So in this case, it's this exponential. So when you do this, it's a good idea to use parentheses, just because this negative, you don't want to forget to distribute the negative. And then this is all set up. So now this is just a regular definite integral to do. So before we get into the integration, let's maybe just simplify the double negatives here. Usually a good thing to do. So we'll be going from negative 1 to 2. We'll have our x squared minus 2x. And again, if we take care of the negative here, that's going to become plus e to the... Now I could leave this as x over 2, but I think it's helpful to kind of rewrite this a little bit. This is one of our special k forms. So I'm going to rewrite this as 1/2 times x. So all I'm doing is I'm breaking this fraction apart. So I have the 1/2. It's kind of like my constant multiple. And then I'm just peeling off that x and putting it next to the fraction. And we've got our dx at the end. All right, so we've got our function. Now we're ready to do the antiderivative. So let's get the antiderivative of the first term. It's 1/3 x cubed if we're doing our power rule. Then let's get the antiderivative of the next term. So that's going to be negative x squared. So far just kind of basic power rule ones. And let's use our k form here for this last. And the k value we can see is 1/2. All right, so how do these k forms work again? Technically it's a u substitution, but we're going to see these a bunch, so let's just kind of remember the formula. So for an exponential function, the exponential term stays the same. So it's going to be e to the 1/2 times x. And then we take that constant k and we flip it and put it in front. So we're going to end up with 2/1, or just 2 in front. So there's our antiderivative. And then we're going to evaluate this from -1 to 2. And now we're ready for the evaluation. So when we do our evaluation, top number gets plugged in first. So when you do this, it's usually a good idea, just set up the framework for your evaluation. So top number gets plugged in, so we'll plug the 2 into this entire antiderivative, see what we get. And then we'll do the same thing with -1, and we'll fill that in here. All right, so get all the parentheses set up, just because, again, it's kind of easy to forget. We're subtracting, so you have to distribute the negative. So if you have the parentheses, you'll be good. All right, so if we get let's plug the 2 in. We're going to get 2 cubed over 3, so we'll get 8/3. Then we'll plug the 2 into the squared, so we get -4. And then when we plug this in over here, we're going to get 2 times e raised to the power 1. So that'll just be 2e. And then we do the same thing with the -1. So we plug -1 in. -1 cubed is going to be -1. So we get -1/3. Then we plug -1 into the squared here. So when we plug that in, it's going to be -1 squared. That's +1, but then we have this other negative in front, so it's going to go back to negative. So we'll have -1. And then finally, we'll have our +2e. And when we plug 1 into the exponent here, -1 in there, we're going to get -1/2. And perfectly fine. Just leave it like that. You don't have to simplify. And if you did, kind of a way to check your work is, if you want to plug this into your calculator, check that it's positive. So because we're doing an area calculation, the area should always be positive. So if you find that if you were to plug this into your calculator and were to find that this is negative, that's an indication that you may be mixed up on the order. Something's wrong. So the most likely culprits are you mixed up the order here, or you mixed up the order here when you actually evaluated. So kind of like a quick check, just make sure the value you get here is positive. All right, so that'll do it for today. And in class, we're going to, try a few more examples like this. So we'll see you then. Bye-bye.